All right. So yeah, thanks for joining seminar again. So today, what I'd like to discuss is about the problem that I shared last time. So we initiate to look at the Hartog triangle in the perspective of invariant metrics. So there are four classical invariant metrics: Keller-Einstein metric, Bergman metric, Kobayashi, and Cartesian metrics of each of them. And Hartog triangle is a well-known as a very important, like the example of clever complex variable and complex geometry. So I'd like to look at more detail, and the perspective we'd like to look at today is the Kähler-Einstein metric. And I assume, so you saw this definition before, you saw some important results before, but I'd like to look at some like the details today together. And here's a primary reference. So let me just share my website again. And if you go to my website, then you can find what I already shared few weeks ago about the note of the Calabi's conjecture. So basically, for the input vector result of the several complex variable, so there is originally there's a result of the Professor Yao in the setting of the compact Kähler manifold from this node. And there's a Cheng and Yao's like also input like the result for the strictly pseudo-convex domain that so how to like solve the complex Monge-Ampere equation in the like the strictly pseudo-convex setting, including complete Kähler like the manifold, and there are lots of actual results since then. So I just wanna go over the note today together. So aiming to understand the Hartog triangle, that paper. So if you look at this paper, so I'd like to interchange two references today together. So I'd like to look at this paper just a bit. And this is the setting of the Hartog's triangle with some generalization. And I briefly went over the first two results because this is the part that I'd like to care, and this is also the explicit like the formula of the Kähler-Einstein metric. And it seems a little bit like the yeah, let me tell the some of the like the remark after I cover some detail of the complex Monge application. So the the detail is here is a little bit overwhelmed if you never look at the Riemannian geometry before. So let me very naively try to explain the setup of the Calabi's conjecture. If you don't get it, in that case, let me know. So the setting would be the following. So for a moment, we assume this M is, let me write down this way. So here, for a moment, we will assume this is compact. I will explain why we assume this compact is because eventually we need to remove this condition. But for first understand, this is very like safe to look at why we first start from here. So compact Kähler manifold, and here J is the complex structure, just a complex structure, so that this is the endomorphism satisfying t squared equals to negative identity, and also it satisfies the tensor condition to preserve the Lie bracket condition. So we already discussed in the previous like a record, so I don't want to go over anything like the as a review. So you can just look at the like the record if you are interested in. So this omega is the Kähler form is defined in the following way. So it is I, a dd bar. Sorry, let me just write down the full description. So Gij bar, dgi wedge, dgj bar. And here's some notational convention. So you might wonder if you didn't look at the heavy computation of the Riemannian geometry before. So there are now two indices. One is I, the other is J. So when we uses the indices, then we need to explicitly declare the summation notation so that it is legal to write in this way. So this is, let us just assume n-dimensional complex manifold. So Ij runs from 1 to n. So this is the correct, like the completely correct notation for sure. But when one proceeds a tensor computation in Riemannian geometry, if one keep all those summation notations, notation becomes extremely ugly. So the convention is that as long as two indices are repeated, then we just assume that should be the summation. This is the so-called Einstein, like the convention. So two indices regarded as summation. So that if you look at this one, two I indices and two J indices. So therefore, we just skip to write it so that we simply just write as a Gij bar, Dgi, which Dgj. Then you should always assume it is the summation. If there's only one single index, then there's no summation. But two indices always it should be regarded as summation. This is a very like a popular convention in differential geometry. So
Is this Einstein summation?
yeah, this is the so-called the Einstein summation. Yep, exactly. So this works not only for the Kähler, but in general, not just the even just Riemannian manifold, but any like the smooth manifold. Is that okay with you? And the intuition is, so we know this matrix is the Hermitian matrix with the, so or I should say in a local coordinate here. So that if you have a manifold, if you basically just have a manifold M, then for each point, then you extract the tangent vector, not the, sorry, tangent space. But because of the complex manifold, like the assumption, so we are not interested in only just the real tangent like the space. We identify this as a holomorphic tangent space. Holomorphic tangent. This can be done if we assume J is a complex structure. And over here, we equip with omega, or you can simply just assume ij bar, so that so for each like the complex like the vector spaces, I mean the holomorphic tangent like the space, so we have a Hermitian inner product so that we can put the geometry on each tangent spaces that determines the geometry of the neighborhood here. And if we will repeat this for arbitrary point, this determines the geometry of the complex manifold. That's the basic like that idea. All right. So after blah blah blah, so that there is a so-called concept of the Lich form that depends on this omega, so that you can simply take this as a definition, so that this is, of course, this is in a local coordinate, but let me just write down as a I dd bar of log of say just a g. So time to time we just write this g as a Riemannian metric. So this just means gi and take the summation. So this is the just as a Riemannian metric. Of course, here we use the inner local coordinate. So from this description, what you can notice is that, so this is what you can see. So if you look at this omega, if you write down this out, then as we already explained, so this is written like this. In this description, you can see that there are two differential forms, Of course, we have a wedge product, so that these two takes two vector fields. So this is differential to form. And when we say this is Kähler condition guarantees that this belongs to the second drum cohomology class. In this case, let's simply just assume this is in R. This is in R because this is just real. So so if you look at the Lich form, so there's a effect of the DD bar. So thereby, so you can see that if you try to write this out, then you have a first like this Hermitian matrix, So and then we would, sorry, I should say determinant of the log. So let me see, let me put determinant. Otherwise, it doesn't make sense to take the log. Determinant of the log. Then if you look at this description, because this is a Hermitian matrix and this is an inner product, so that all eigenvalues are real and positive. So determinant is always positive. So this is a real positive like the function, so that it makes sense to take the log. This can be taken. And we can now take this guy again, this guy again. If you write it out as a complex like the Haitian, so and there's a just effect of this guy because we know exterior derivative can be decomposed as a partial d plus partial d bar, so that you can also see the effect of it also takes two vector fields here and here. And of course, there's a I here to make to the real form, so that it makes sense. It makes sense to also compare with the Kähler metric. And you can also see, I should write the bracket notation to represent the representation in the ground common class, so that this also makes sense. So this also belongs to the second drum cohomology class. These are guaranteed. Is that okay with you? Because so as long as we define this as a partial d bar, so if you just put the exterior derivative here, then this guarantees this guy, then you can check this just should be zero always. So that you can now observe in this setting up to here that Kähler metric as a Kähler form always belongs to the second drum cohomology class. This is the definition of the Kähler metric. When we say omega is Kähler, then it should be D close. So this always belongs to the second drum cohomology class. And from the description of the Leach form here, so this always also belongs to the second drum cohomology class. And up to here, you can see that we didn't use any assumption of the compactness of the Kähler manifold. So that you might wonder, so where did we really need to use the compactness? So can you find where actually we are assuming the Kähler the compactness condition? What is the usage? Can you imagine? This is the very nice question. This could be helpful a little bit. So where did we use the compactness? I want you to imagine very naively. So if you have any idea, let me know. Any ideas? So let me give you the hint. It's related to the drum cohomology definition. So a little bit inconsistency is that when we talk about the drum cohomology, then we look at the exterior derivative, usually D, but now we are looking the complex manifold. So that's why we decompose exterior derivative D as a partial D plus partial D bar. And it seems like in a way, if you look at the Leach form with respect to omega, so because of the like the nature of the partial D bar, it is D closed. That's what I said. And thereby it is the element is the drum cohomology class. But there is a certain inconsistency regarding the exterior derivative and partial D bar. Of course, they are related. So my question is again following. So where is the compactness? So this question is important in a way that for the several complex like the variable, like the community, we mostly just look at the bounded domain without the boundary. So those are always non-compact. That means that the sum behind assumption cannot be applied directly. This is a part of the reason why we always look at the Bergman metric. But can you kind of See it? Let me explain. This reason is very deep, very, very actually deep. So the reason is so-called the D-bar lemma. So please keep this in your mind. So if there are some like the extension of the work in the setting of the symplectic manifold, always this assumption is most crucial so that you can simply just ask always the speaker that where's the DD-bar lemma. So this lemma fails for non-compact. So this fails for non-compact manifolds in general. And this is a consequence. This is a consequence of the Hodge theorem. Not Hodge theorem, Hodge theory. So I will not go over the proof for today. If any of you request, I'm very happy to do so, but not at least not today. So M omega compact Kähler manifold. So this condition is crucial. So without compactness, we cannot state this guy. So here's the setting. So if omega, so you can just think those like the two elements are the previous like two elements, and eta are two real one-on forms in the same cohomology class. So we are now using something special in a way that if you look at the Leach form, that is one form. One form means one like the differential form, there's no the complex like the conjugate. The other one, there's a complex conjugate, but take the wedge. So this is special differential two form rather than just a 2-0 form or 0-2 form. We just look at such types of the forms. So if you look at these two, so you can just assume this is indeed omega. And if you just assume this is eta, so that they are written as a so-called one form, one form. Of course, we cannot say yet that omega and each of the omega belongs to the same cohomology class. We cannot say yet. But if we assume that's the case, then from the second term cohomology, so originally, so this guarantees that because omega eta belongs to here, for example, right? So then this is same as, so and we say omega eta are the same, so that it guarantees in general, without this like dilemma, this guarantees that if you look at the difference, then there must be the function. So let me write down. So this function notation could be not that good. So for some alpha, differential one form. This is definitely guaranteed because they belong to the same second term cohomology class. So there must be differential one form that exterior derivative D should realize this difference. That's the just definition. So, but this is not what the lemma says. Then we'd like to say, then there exists function, which is real valued, such that the difference is written as I dt bar of it. So that we can find the same like the type of the difference. So this is crucial because if you try to compare omega with the reach of the omega, they are not just a differential two form. They are one form. So that if we want to compare, as long as they if they belong to the same cohomology class, then we'd like to actually make the difference as a one-on form as well. In order to do it, we need to guarantee that the difference can be also written as just dd bar of partial d bar f, not just the d alpha. So this like the lemma is in that sense very crucial. We'd like to make the same type. Yeah, Josephine.
So that alpha is a scalar, right? Because
So here, because omega and eta are all differential two forms, and if they belong to the same second term cohomology class, then alpha must be differential one form. So that if once we take the exterior derivative again, it becomes differential two form that realize the difference. Otherwise, left-hand side doesn't make sense. Left-hand side is already differential tuple, right? Could be exactly zero,
Yeah,
but the
yeah,
difference is just a difference tuple. The alpha should be differential one.
yeah. Thank you.
Sure.
Yeah, here I have a small um, doubt. So this DD bar lemma is true for locally, right? Is
So
it?
that's also
Is
very
it
like the
true?
important like the issue. So if this is local statement, this is not interesting.
I see.
So locally, this
Yeah,
always
what I,
work for non-compact like the Kählers. So here
yeah,
important,
yeah, yeah,
yeah. This is that's very
yeah,
important. This is global. Global really
yeah.
a smooth function.
But it is true in locally, right?
This can be taken always locally without any assumption on Kähler manifold. So Kähler
Yes,
metric is
yes,
always
exactly.
complex Hessian of the Polaris subharmonic function, but
Okay.
always just locally. That's always
So
guaranteed.
by
Yeah.
using the compactness, we are extending
You can kind
globally
of
to,
thinking that way. Yep.
yeah, okay.
Yeah.
Yeah.
Locally, always we can realize the Kähler metric is a complex Hessian of Polaris subharmonic function. That's guaranteed. But with the now the strong assumption of the compactness, so the always the difference can be written like realized in this way. So in that sense, this is very powerful. So
Okay. So is there any reason why it is not true in non-compact space?
just a Hodge
Because see,
theory just didn't apply for the non-compact in general.
I see, I see. Okay. So what I'm thinking is that, so since it is locally true, so we can use partitioning of unity so that we can extend for globally. Is
That's
it
very
correct?
like the important like the question. So it turns out to be no because of the rigidity of the holomorphic function. So for example, so yeah, that's so what bear this like a question. This is very important question. That intuitively very makes sense. So let me say bye. Ready? So why we can't extend local data to global ones in general. So it seems we always have a partition of unity. So partition of unity guarantees that as long as we have a local data, then we can simply just glue them all together. So why these are not guaranteed? So the answer, so because of holomorphicity. So if you imagine about the, for example, the like the situation, so if you have a holomorphic function, so say M to R holomorphic, such that, so if you restrict this function to the small neighborhood, and if you just assume this is zero for some small neighborhood, what happens? This f must be zero everywhere.
Yeah, exactly. It's
So
identity theorem. Yeah.
so that we cannot use the like the partition of unity for the holomorphic
Yeah.
functions. This is not guaranteed. So it's very important to just understand because of that, that then how can you really just extend the local object to global object? So so-called the analytic continuation
I
should be
have a
completely different
multiple
issue. Continuation. So that this requires so-called the ship theory. So for example, I will not talk this today that much, but so the more of the canonical way is that, so because I need to introduce a definition of ship, but if any of you request, I'm very happy to do so. So there's a so-called exponential ship of this short exact sequence. So this is just the inclusion. And this is the exponential of the 2 pi I with the function. So that if you choose the, just this O sub x just means the shape of the holomorphic functions. So for each open subset, so we just look at all holomorphic functions. And if you just map this to the, just the e to the 2 pi if, this is non-vanishing holomorphic ones. non-vanishing all of functions on U. Then the issue is that, so because we use the exponential function and we know the inverse one, which is the logarithmic function, complex logarithmic. In order to define the complex logarithmic one, we know there's an issue of the branch cut. So the procedure of taking this inverse uses the log, and in order to do it, we need to take the branch cut. Otherwise, the angle is not defined uniquely. And in order to define this, then we need to restrict to the open subset, meaning that we need to take the branch cut so that we cannot overcoming in general this like the effect of the branch cut, so that we can only extend the object with some kind of restriction, so that one should like to wonder then how can do it. Then this requires the ship theory. So let me just write down. So this is a short exact sequence, whatever the definition is. Then this induces the long exact sequence that gives us H0 of XC, H0 of OX, H0 of sky, and goes the next stage. So, and in this way, there's a way to like extend the local object in terms of the ship cohomology. But this is the very important like, subject in complex geometry for sure, but it just takes time to really explain. So if any of you are interested in, then in that case, let me know. But not just today. I just want to just introduce the complex non-geometry equation today. So anyhow, let me just summarize what we have discussed. So if we look at the compact Kähler manifold setting with two real one-on form. One is the Kähler form itself. This is a real one-on form. Another one is the Leach form. These are all differential two form, but more special. These are real one-on form. So that if we just apply the perspective from this Didi-Bar lemma, then if they belong to the same cohomology class for these two real one-on form, then not only realizes the exterior derivative of the smooth differential one form by the definition of the drum cohomology like the class, we can realize it as a partial d bar of the smooth function which is defined globally. But this is not guaranteed. So with this perspective, if you look at think about the definition of the Bergman metric, what happened? We have already globally defined Bergman corner. So therefore, we already use sort of the cheating that this object is already globally defined. The behind reason is that in general, we cannot find such an object. So Bergman corner is in that way very special. And when we compare the Bergman metric with the Kähler-Einstein metric, so that we are kind of expect something similar. Kind of. But we know in general, we cannot define some object globally to just realize the object we care as a complex Hessian of the global object. So, but this is what exactly we'd like to do. All right. So let's now move on to so I'm looking at the Calabi's conjecture, I mean the note that I share. So details are there. So if any of you would like to go over the detail and ask me a question, I'm very happy to do so. So now you can find the following. So definition. There are several the equivalent the characterization of the first Chern class from the Chern-Hodge theory and also the characteristic class perspective and so on. But this is, I think, most likely concrete. So we start from M omega, compact Kähler. Now let me also even skip to mention about the complex structure. That's already assumed. So we have M omega. So that now we have Leach of the omega for sure. So Leach of the omega, so that belongs to the H2 from cohomology class. This is guaranteed. So now let's just assume let me just use the notation from my note, be another Kähler form on M. So why not? We can just look at another Kähler form if that's possible. So that this induces this for sure as also drum cohomology like the element. That's guaranteed. Why not? Then the special the control is that actually we know how to write down each of them, how to write down each of them so that we know this can be written as I dd bar log of determinant of G. So G is just a Riemannian metric of this omega. So let me just write this just G. Is that okay with you? So this is good. This is not that clear. So okay. So what I'm saying, omega as a I Gij bar EGI wedge EGJ I EGJ bar. So this is good. And let me also write down this guy as a I Hij bar DGI wedge DGJ bar. Of course, this is inner local coordinate. Up to here, so far so good. Then, so if you have a question, let me know. That's absolutely fine. I can discuss anything further. So that then we just take the determinant, and take the log that becomes the determinant of the Hermitian metric becomes real. We can take the log and we can take the bar. Similarly, we can also do this. We can also do this. But the expression of the right-hand side depends on the each like the local coordinate. Once we choose the local coordinate, then we can do it. That's what I'm so let me write down more precise expression. So this just means we can write like this. For sure, in a local coordinate. So that without the local coordinate, we can write each of them as a d I dd bar log of determinant of G. And with H, we can play the same game. But you can just assume if you take the local coordinate, we just realize the expression. And if you change the coordinate, there's just an effect of the changing the coordinate, just that's it. So that we can write like this. So that what we can do is you can take this subtraction of these two. Let's try to just subtract these two objects. So where's my cursor? Then lich of omega minus lich of h becomes what? I dd bar of log of determinant of g divided by determinant of h. Is that okay with you? So if you feel you do not like this, like the notation, then you can write this as I you can write it like this in a local coordinate. Is that okay with you up to here? So let me be clear. So this expression and this expression are using the some local fixed local coordinate for sure. And therefore this also works for the same local coordinate expression so that you are now thinking. So now this is some like a deep observation. So think about this carefully. So we start from the complex manifold. So we are looking at M, but we can just restrict to the just the open subset. In that open subset, so these two and this expression are legally allowed with respect to that open subset for sure. Are you with me? So suppose now you change the U open subset U to open subset V with the overlap, then then why we need to change it. We need to change it. So what's the effect of the changing the coordinate? You need to put like something like P transpose P, something like this, and take the determinant so that there's an effect of this guy. But what do you know? You should have the same effect on denominator. So what happened? They will be canceled. So that we know the effect of the changing the coordinate will give you the, so what do we call? So like the form of the like the A, B, A inverse or A, B, A transpose, that kind of the form, right? So in general, as long as we change the coordinate or the overlap, then we need to consider that effect, but because of the ratio expression of the log, so those effects will be canceled together. What does that mean? Once we define locally, so if we take the another open subset with the overlap, this expression should be exactly the same. So for each overlap, as long as they're the same, we can extend globally. So this is very like the subtle that if we have just this expression, we cannot change it globally. That's not guaranteed. But the subtraction is actually globally defined object, especially here. It looks local object, but it is not. It is a global object. Are you with me what I'm talking about? So now this is a sort of the converse direction of the DD-bar lemma in a sense that if we have two like the differential two forms in the same drum cohomology class, then we can realize as a DD-bar of the globally defined smooth function. But in the case of the Lich forms, this is always guaranteed in this way. So what I'm saying here is that this observation give you this guy satisfying this condition. What does that mean? So this guarantees those two must be in the same cohomology class because the difference can be realized as a DD-bar of the globally defined smooth function. Are you with me? So the definition. So we define this guy as a first Chern class. So you can now see this notation, I mean the subtlety in a sense that I didn't even specify the Kähler metric because this is a topological object. So that this HC1M belongs to the second drum cohomology as a representative. And in general, this belongs to Z, but for the sake, for the non-compact case, let me just write this as MR. But this actually coefficient, actually Z coefficient. So let me just repeat. So you can simply now think this way. So this condition is very like the subtle. So let us start from the compact Kähler manifold. So when we say compact Kähler manifold, it always equips with the Kähler form. If we have a Kähler form, we have a Lich form. We know Lich form is declosed. So just take that like the representative. That's the definition of the first Chern class. So what's the subtlety? Whatever Kähler metric that you choose, they are the same. This argument shows that, right? So it doesn't matter which Kähler metric that you choose, as long as the Kähler metric is defined, it does not even require the completeness. It didn't require anything. As long as you have a Kähler metric, then you know this is the close for the Lich form, then just take the representative in the drum cohomology class. Then this is actually a unique one. Then that's we call it by the first Chern class. That's the definition. So any questions here? So this is most important like the object to understand the Kähler-Einstein metric. Just a loop here. All right. So in general, so I actually telling you a little bit lie in a sense that so this is not exactly pi C1, but multiply by 2 pi because of the Gauss-Bonnet theorem. So yeah, so there's a behind reason. So up to like the scaling, so we actually take that as a 2 pi dividing. So now we are ready to understand the statement, the Calabi's conjecture and the complex Monge-Ampere equation. So now let me go back to my note if you guys have no questions. So these are full details about what I actually skipped to just write down why Lich form is looking like this. And so I skipped to write the negative sign, sorry for that. So but it doesn't actually change the primary conversation. So Calabi's conjecture is the following. Calabi's conjecture says, so start from the compact Kähler manifold. So this is the statement that I need to just explain as that's a major like the statement. So what we said is let's just choose any of the real one-on form. Any of the real one-on form. So make sure that this is any. Then what we'd like to claim is that there exists a scalar metric whose Lich form recovers this omega, and they belong to the same cohomology class. That's the Calabi's conjecture. Let me just repeat. The setting is compact Kähler manifold. So we have already Kähler metric. We already have a Kähler metric, so that it makes sense to talk about the first Chern class. First Chern class is the one representative, so just the element of the second drum cohomology class. Then let's choose arbitrarily real one-on form from this class. Then what we'd like to find is the Kähler metric that exactly recovers this rho as a Lich of the omega. But omega naught, which is an initial metric, the omega that we'd like to find, they are in the same cohomology class. So that each of the, so if you very naively say it, the real one-on form we'd like to realize as a Lich form. That's the Calabi's conjecture. So there's no like the bracket notation here, so that we really want to realize this guy as a Lich form of some Kähler metric. So do you understand the spirit of the Calabi's conjecture? So that it's sort of the inverse. So if we have a Kähler form, then we know Lich form. Lich form is a real one-on form. But we'd like to do the converse. We pick up arbitrary real one-on form. Of course, in this like the first Chern class, because this is also that's one of the necessary. We cannot get so because if this is the case, then this rho should belong to the same first Chern class for sure. This is also necessary to do it, but we are just looking the opposite, like the converse direction, that if it should start from real one-on form, I mean any, then in fact, it turns out that we can always find unique Kähler metric that it is realized as a Lich form, and they belong to the same round cohomology class. So if you have any like the questions or comments regarding this like the statement, this is now completely solved by Xingtong Yao in 1978. And Cheng Yao's paper and all those bounded domains are just extending like this like the conjecture to the non-complex settings. Any questions? So that's why I need to first introduce the first Chern class in the beginning in order to say this like a statement. So there's the one like the subtlety. So this conjecture is completely solved by just taking so-called Monge-Ampere equation. Monge-Ampere equation. So this is already written over here. But it might be hard to just read each line by line. So let me just
Yeah, I have a question here.
Sure.
I have a question. So the Calabi conjecture says some correspondence, right? One correspondence between Chern class and the metric,
the
right?
Kähler metric. Yeah.
Class, yeah. Okay. So is it possible to conclude that if the second rank of a DRAM cohomology group is I mean equivalent to like 1-1 form. I mean, did you get?
So
So
can
is
you
there
be
any
more
equivalence
precise?
between second homology group of manifold? Is with sorry, is there any 1-1 correspondence between second rank DRAM cohomology group with the 1-1 the homology group of 1-1 form?
So let me try to draw the situation. So if we have a compact Taylor manifold, so that we know, so this Lich of omega is the close real differential two form.
Yes.
This is guaranteed, and it's just written as a I d bar log of determinant of just a G. This is the description. Okay, so that we can take the representative in the second drum cohomology class. This is guaranteed. So that we just write down let me just look at my note so that we just take just division by dividing by 2 pi because of the Gauss net that so if we take the integral of this like the differential one on form on the compact Riemann surface, this becomes just a Euler characteristic. That's why we divide by 2 pi. So this actually is this is the definition of the first Chern class. And what we observed was, so if we choose another Taylor metric, say H, they must be the same. That's what we observe for any Taylor metric H. Is that okay with you up to here?
Yeah, yes.
So that's why it makes sense to talk about the first Chern class in the like the Calabi conjecture statement. The given setting is already compact Taylor manifold. So in this stage, already the first Chern class is clearly declared. Is that okay with you? Because as long as we have a compact Taylor manifold, then C1M is already defined. Is that okay with you?
Different.
And if we choose
Yes.
any of the Kähler metric that we'd like to find some desired property. So whatever Kähler metric we choose, it always make the same first Chern class. There's no other like the possible like the cases other than rather than just this one. So that we want to know for any real one-on form, but we'd like to realize this real one-on form as a Lich form. So that for this one, we should say this belongs to 2 pi of C1M. So if this condition is not satisfied, then we cannot realize that Lich form. That's not possible. That's what previous argument already says. So this one, we'd like to say there exists unique Kähler metric omega such that this Lich of omega is rho and yeah, so let me say just let me write down just this and just this one. Is this clarify your question? So I'm just saying about the necessity of the first Chern class condition. So because if our goal is to find the Lich form of the sum Kähler metric, then it must like the hit the like the first Chern class because of the previous like the argument. So that we should choose the element rho from C1M up to 2 pi. Is that okay with you? Any other questions or comments? I think this is the most important like the statement in complex geometry, in my opinion. So every like a business initiates from this like this statement. So if you have no questions, then let me just copy and paste what I wrote in my note already, so that then how can we solve this like the conjecture? How can we solve this conjecture? I'm not saying this is sufficient, but this is necessary and sufficient at the same time. So what one want to do is the following. So in order to solve this approach, so today let me just go over up to here. So let omega belongs to 2 pi C1M, any real one-on form. But we know such that, so this guy, the representative, and this guy, the representative, we know they must be the same. There's no other like a possibility. Is that okay with you? So because we already choose from here. Are you with me? So the representative must be the same. There's no other ambiguity up to here. So then what can we say? We know Dirichlet lemma. So if you look at the Dirichlet lemma again, what Dirichlet lemma says is that if omega and eta belongs to the same cohomology class, then we know we can realize the difference as a complex Hessian of the globally defined function. That's guaranteed. And this like the condition is not satisfying for non-compact in general. So that we can now apply at least the lemma in this setting because we assume our manifold is compact. So that's how the compactness here plays a role. So now let's just apply the lemma. So eventually the function in the as a solution of the Monge-Ampere equation is different. So let me just use the same notation from my note. So we are able to find at least one smooth function defined on M globally. This is guaranteed, such that rho minus leech of omega naught must be I dt bar of F tilde. And for the just the consistency, let me just keep the same negative like the sign. Doesn't really matter, right? So because we are looking for some of the some function. So now this is guaranteed. All right. So now what I'd like to do is I'd like to introduce the constant that I'd like to control. So the C is prescribes constant that I'd like to later just declare this constant should be this value. Then what I'd like to do is I'd like to take the integral of this e to the f. This is some function, and M is complex manifold. M is complex manifold, so this is very defined. So and this volume is taken from the initial metric. So this is definitely guaranteed. Then if you write it out, this one, so that we can take this e to the c in front of it, so that we can simply just take e to the c integral of this one. And here you can also see that we also use the compactness here. Otherwise, we cannot guarantee this value is finite. So for the non-compact one, we need to really careful that whether or not we can handle this guy. So now what I'd like to do is I'd like to choose the C here in a way that it satisfies this condition, or precisely just the volume with respect to this metric. Is this guaranteed? Yes, it is, because those are finite, like a positive, like the values that we're absolutely able to find such a like a C value uniquely. So this is now guaranteed. So what Yao did is, if this condition is satisfied, then there's a some function. So now Yao's theorem plays a role. So Yao's theorem is applied under this condition that there exists unique function which is real valued such that it satisfies three conditions. Number one, so if you take the integral, this is 0. This is for condition. Second condition, if you just write this out, this is the omega we'd like to find. This is realized as omega naught plus I dt bar of this per phi. So this is a desired Kähler metric we'd like to find. 3. So if you look at the n times wedge product of this omega, and n times wedge product is omega naught, so this is exactly realized by this guy. And if you write down this third equation is just same as this part is, so this is e to the f determinant of g ij bar, because this is an NN form, so that we can just cancel those two same NN form from the left-hand side and the right-hand side. So this just becomes ij bar plus second derivative of the Murphy. We'll get this explained. This is the complex Monge-Ampere equation. And also there's a version of the parabolic one by introducing the time parameter t, that's the Kähler-Leach rule. So Yao's theorem tells that you can find the unique smooth function per phi satisfying these three conditions. Then you might wonder, then why this is sufficient and actually necessary. So the reason is, if this is the case, then let's just try to see, need to check. For omega, that is defined as omega naught plus I dt bar of bar phi. So we need to know which of this omega recovers omega, recovers rho. This is what we need to check. So now let's just apply what we already know. We already know this is the case, right? Rho, let me just copy, satisfies this equation. So indeed, we start from here. We start from here. So this is equivalent to say rho equals lich of omega naught minus I dt bar of just f tilde. But we can just replace this by dt bar of just f because we just add by just constant. This is our guarantee. So then now let's apply the third condition. Third condition guarantees that, so we know, where were we? Where were we? Third condition guarantees that, so this guy is actually the volume. This guy is the, sorry. So this guy is what? So I dt bar log of determinant Gij bar. It's okay with you? Lich of omega naught is same as just this guy. Sorry, actually I changed many signs from the beginning. I actually should apologize. So because I actually do not try to even memorize the. So in fact, I make all that's the errors in the very consistent way. So actually there is a negative signs here from the beginning. Negative sign here. Let me just change everything here. Yeah, hard negative signs, truth be told. Yeah, let me just look at my note again. Just hang on. I'm just trying to remind myself. I think I can do it. So let's start from here. I think up to here we are good. Is that okay with you? Up to here we are good. So from here, what I know is by two, it could be a little bit different from my note. So this omega is this guy. This guy. So this is the same as Gij bar plus this guy in local coordinate. So that I'd like to take the wedge up to n times. That will give us determinant of this expression. So we will get determinant Gij bar plus this expression up to dg1 wedge, dgn wedge, dg1 bar wedge, dgn bar. We'll get this. This is nn form, so that we can now take the this part, so that we can take the log. I'm just applying just the log determinant of this expression. So we can take the log and we can take dt bar and I. So we know this coincide with the lich of omega already, lich of omega. Then by using 3, we will get, sorry, it's a little bit hand waving. So I'm just applying just a definition. So let me just share my note. I know what I do is correct, but I kind of feel, yeah, it's a little bit not good. So once we get this, like the condition, it's just using just a definition, using the definition, then one can just check this condition is satisfied. Yeah, sorry for that. I actually didn't just prepare it. I saw how to just present. So yeah, this recovers the just Calabi's conjecture by just solving just these, just finding this like a unique function satisfying three conditions. So now the Calabi is like the conjecture is completely solved. Then what is the Kähler-Einstein metric? So the Kähler-Einstein metric is slightly different like the issue. So what we'd like to find is such a like the Kähler metric. Make sure that this is different like the condition. We start from the initial metric in some way. Initial metric that's satisfying this condition at the same time. So it does not mean that we start from rho, then we'd like to find the Kähler metric satisfying each of the rho omega equal just becomes just a rho. We'd like to make these two conditions to be satisfied at the same time. So this is a completely different issue. But still the Gauss like the method works, like the same way for the negative curvature, negative ridge curvature, and also the zero curvature, but not for the positive curvature. Positive curvature doesn't work. Then the class of boundary is completely different like the story. So I'd like to just today finish my very like the bad explanation with this like the paper. So in this paper, so the subtlety is the following. So what's the subtlety of the Dirichlet lemma and the complex Monge equation? So indeed the usage of the Dirichlet lemma. So we are not guaranteed to use in general. So for this, like the Hartog triangle here, the subtlety is that they already start from the globally defined smooth function. This is in general not guaranteed for general non-compact Kähler manifold. They just start from giving such a like the potential function in the beginning. Then we can play the same game. So this is more in some sense crucial. So that if we want to modify this expression for our own purposes, then we need to just modify this expression. This is most sensitive like the information. Then once one get that, now you see, so this is now the expression of the Kähler metric, which is defined globally, as long as this is defined globally. And this is now the condition of the Kähler-Einstein metric. So this is one-on form, and we know from the construction of each form, this is one-on form, so that time to time we are able to compare by some real value constant lambda. And if this condition is satisfied, that we call such a like the omega Kähler-Einstein metric. So the subtlety is that, so if we start from here, then you have the expression of the Kähler metric also explicit and defined globally. And as long as you have such a like the Kähler metric, then you have also global description of each one-on form, then you can compare these two real one-on form. Then if this condition is satisfied, then that's that can be also realized as solution of the Monge equation in this special form. Then what can one do? One can just check whether or not this condition is satisfied, right? And they just look at the condition that this condition just satisfied, and this is just a global potential for their like the Monge equation. So how could they solve this? Not estimate, just a plugin. So if you just look at it, so make sure that we know the global expression of the Kähler metric in this like the context, so that we can take the determinant computation. Is that okay with you? Computation. So or just computation, and just compare. That's it. So nothing heavy estimate in this like context. So that's the end of today's my very like naive introduction. So if you guys have any questions, let me know.
Yeah, is it simple to work with just a vertex triangle in 2 dimension?
So if you look at just an ordinary Hartog triangle, that means we are not carrying other components. We just assume m equals just a 1. M equals 1. So there's only one component here. And for 2-dimensional like the Hartog triangle, we just also assume k equals also 1. And this is not just a norm square, but indeed just the absolute value of the square,
The modulus,
ordinary
yes.
1. So just k and m just equals 1 in the previous case. Then all those will be simply just drop out.
Okay.
Simply all of them.
Yeah, because the vertex triangle is bivolomorphic to D star cross D,
Yeah,
right?
D star cross D, exactly.
Yeah, so we can pull back all those things from there, right?
Yeah, I think that's the way how they come up with this like a potential function.
I see. Okay.
So then once they got this expression, then they are able to describe one Kähler metric, and by just applying the known theory, this metric would be just a complete. And they just check the condition of the Kähler-Einstein metric condition, and some of the cases it just works. But for the two-dimensional case, it might not work. So one can still check, right? One can still check. But we have a little bit different like context for looking at like this
Yes.
construction. All right. So if there's no other questions, so sorry for my very like the sloppy explanation, because I'm not good teacher in the sense that I'm very like the lazy to really just digest everything, because you guys are already I know capable, so I just try to explain just kind of a big picture. But I know I'm just lazy. So if you guys request to understand anything detail, I'm very happy to do so, but not everything. So yeah, let me today stop the record here.